Hi everybody, welcome to our next segment discussing differential equations as a prelude to the Laplace transform. In particular, this time we're going to talk about non-homogeneous linear second-order ordinary differential equations. Alright, so what is the form of such an equation? Well, it's going to have a form that looks like a of x onto y double dot plus b of x onto y dot plus c of x onto y equals d of x. So this is probably not too surprising, and if you recall what we had before, when d of x was equal to 0, we said the equation was homogeneous, and when d of x is non-zero, then it is non-homogeneous. Okay, so d of x is not 0 for the non-homogeneous case. Also, we're going to deal entirely with constant coefficient equations, and that really means that a of x, b of x, and c of x are going to be constant. So we do know that a of x is going to be constant and non-zero. Okay, so because if a of x were 0, then we wouldn't have the y double dot term and we wouldn't have a second order equation. Okay, then b of x and c of x. B of x and c of x are going to be constant. And that does, in this case, include the possibility of having b of x or c of x be 0. Okay, so we have a major important fact to discuss that will let us deal with some solution methodologies for these non-homogeneous linear second-order equations. Okay, so basically suppose that y equals f of x is a solution to the homogeneous system, or the homogeneous equation. Okay, so if f of x is a solution to the homogeneous equation, it is a solution to the system ay double dot plus by dot plus c equals 0, right? The right-hand side has to be 0, or the d of x term is 0. We already know how to generate solutions for those cases because we discussed those in the previous lecture. Now, we want to further suppose that y sub p equals g of x is a solution to the non-homogeneous case. Okay, so yp stands for the particular solution to the non-homogeneous case, and I can actually put a little h on my y of h to denote that it's a solution to the homogeneous equation. All right, so if we have those two situations, then y of h plus y of p, which is going to equal f of x plus g of x, is a solution, is a general solution to the entire non-homogeneous differential equation. Okay, so that's going to help us with solution methodology, so that's why we're pointing that out. Okay, so now as an example, let's look at this equation here. So we've got y double dot plus 3y dot plus 2y equals 2e to the 3x. Okay, so this is our d of x. right? So it's the right-hand side. It is not 0, so we have a non-homogeneous linear second-order ordinary differential equation. Okay, so to make it very clear, we point out that the homogeneous system, or the homogeneous equation, is going to be y double dot plus 3y dot plus 2y equals 0. We can write the characteristic equation, which is going to be r squared plus 3r plus 2 equals 0. And we know we can also write that as r plus 1 onto r plus 3. Okay, so we can factor that pretty easily. Okay, so we can tell by inspection that we're going to have the roots r1 equals -1 and r2 equals -3. So our solution to the homogeneous case, the general solution to the homogeneous case is going to look something like y sub h equals f of x equals c1 e to the minus x plus c2 e to the minus 2x. Okay, and that, again, that solution method comes from our prior discussion on homogeneous equations. Okay, so now to deal with the particular solution that helps us handle the non-homogeneous situation, we take a look at the form of the right-hand side. So we go back up here and look at d of x, and we see that it is something that is an exponential function. All right, so we're going to, again, sort of guess at a solution, but we're going to do so, again, with intuition. And so we're going to presume that our particular solution, in this case, y sub p, is going to have some form a e to the 3x. Okay, so if we presume that, then maybe we can work with it. So if y sub p is a e to the 3x, then the first derivative, y dot of p, is going to be 3a e to the 3x, and y double prime is going to be 9a e to the 3x. You may say, well, that's great, but how do I deal with that? Well, let's take a look. Okay, I've rewritten the differential equation along with the y sub p and its first and second derivative. And now what we want to do, we're going to employ something that's called the method of undetermined coefficients. To employ the method of undetermined coefficients, we're going to plug y sub p and its derivatives into the original differential equation. So when that happens, the y double prime term, well, that's just going to be yp, right? Yp double prime, and then we're going to plug in plus 3 onto yp prime plus 2 onto y, and we're going to see what that equals. Well, that's going to give us 9a e to the 3x plus 3 onto this, which is going to give us 9a e to the 3x. And then finally, plus 2 onto y, which is going to give us plus 2a e to the 3x. Okay, and then that is going to equal 2e to the 3x, right? And we know that because that's what's written up here. At least it has to equal that. So what we need to do is find out what value of a actually makes that happen. All right, so we can go into this expression here, to this entire expression here. We can divide through on both sides by e to the 3x to get rid of the exponential term, and we're just going to be left with 9a plus 9a plus 2a equals 2. Okay, so what we're going to do is determine what those coefficients had to be. Well, we can add all this up together and we will get, right, so when we do that, we get 20a equals 2 and that tells us that A equals 1/10. Right, so that's going to be our now determined coefficient. And so then we can go back and we can rewrite y sub p, the particular solution, as y sub p is going to be 1/10 e to the 3x. Okay, so that is our particular solution, and then we can take that back with the general solution, or with the, the homogeneous solution, to come up with the entire general solution. And I'll go ahead and just write that down here. So I'm just going to write that our general solution, y sub g, is going to be, if you recall, we had the homogeneous solution C1 e to the negative x plus C2 e to the negative 2x, and then now we're going to add this particular solution, so we're going to have plus 1/10 e to the negative, e to the plus 3x. So 3x. Okay, so this is the general solution to the second order equation given at the top. And so we still have these undetermined coefficients C1 and C2, but these would be determined using initial conditions in the same manner that we employed in the prior discussion on homogeneous systems. So we're not going to dig into that particular thing here, but we do have at least now a way to deal with a case where we have a non-zero right-hand side that has an exponential form. All right, so next we're going to move on to a case where the right-hand side is of a different form. Okay, so now we have a different example. It's very much like the prior one, except we've just changed the right-hand side. So it's not an exponential function. It's just what looks like it's a quadratic term, so a 4x squared. So it looks sort of polynomial-like. The left-hand side, I left the same, and it's because when we want to keep finding the solution to the homogeneous case, and rather than just battling through different solutions, we already know the solution to the homogeneous case for this. So the homogeneous solution is going to be y sub h equals c1 e to the minus x plus c2 e to the minus 2x. Okay, so there's nothing new there. We just want to keep that in mind. And we're going to reuse that again in the next example. So don't be surprised by that. But now, again, we're going to employ the method of undetermined coefficients. And rather than choosing exponential functions, it wouldn't make a lot of sense to do that because we're going to have other e to the x terms show up in here. So it makes sense. Actually, we're going to choose something that looks like y sub g equals ax squared plus bx plus c. So essentially it looks like a polynomial, right? So it's similar in form to the right-hand side above. Now obviously it has more terms in it, but what we need to do now is determine if that is the solution, what are those coefficients a, b, and c. All right, so the first thing we want to do to deal with this is look at the derivatives of y sub g, right? So we're going to have y dot sub g is going to be 2ax plus b, right? It's just the derivative of this expression. And then y double prime of g is just going to be 2a. Okay, so now why do I do that? Well, let's plug yg dot and yg double dot into the original differential equation. So we'll start with y double dot, and so that's going to be 2a, and then plus 3 times y dot, so it's going to be 3 onto 2ax plus b, and then plus 2 onto y, so plus 2 onto ax squared plus bx plus c, and that had better equal 4x squared once we find out what those coefficients are. Okay, so now we got to do a little legwork and collect terms and reorganize this expression. Okay, so when we do that, we're going to collect the x squared term, right? So we have the x squared term is going to be 2a x squared, right? That's the only x squared term. And then we're going to have some terms that are going to be multiplied by x. Okay, so if we look, the first term doesn't involve x. This one involves a 3 times 2ax, so it's going to involve a 6a. And then another term that involves x is bx here, so we got 2bx. So 6a plus 2b all onto x. And then we want to look at the terms that don't involve x at all. And so we have a 2a. Okay, so we can collect those together. 2a, we have a 3b. And finally, we have a 2c. Okay, and again, that still has to equal the right-hand side, which is 4x squared. Okay, so now we've got to compare coefficients on the left and right. So obviously, if the coefficient for the x squared term on the right-hand side, it's 4. On the left-hand side, it's 2a. So what that means is 2a equals 4, and that tells us that a must equal 2. Okay, so that's not so bad. And then we also know that 6a plus 2b, well, that's going to be a coefficient for an x term, and there is no x term on the right-hand side, so that must mean that 6a plus 2b equals 0. Okay, so that's 6 times 2, so that's 12, plus 2b equals 0. Well, we can tell by inspection then that b equals -6. Right, and then finally, we deal with this one. Also, there is no constant term on the right-hand side, so this must add up to 0. So we know that 2a plus 3b plus 2c equals 0. So I know that 2, I'll write it this way, 2 onto 2 plus 3 onto -6 plus 2c equals 0. All right, so what do we have here? Then we have 4 here plus -18, so that's going to be -14. We take that to the other side. We know that 2c equals 14, and therefore c equals 7. All right, so now we have coefficients. A equals 2, b equals -6, and c equals 7 that will be used in this expression. Okay, so we can just fill in for the particular solution. We can just say that's going to be 2x squared minus 6x plus 7. So now we have the solution, the general solution for the homogeneous case, and the particular solution for the non-homogeneous case, and that gives us the total general solution, which is going to be y sub g equals c1 e to the minus x plus c2 e to the minus 2x, and then plus 2x squared minus 6x plus 7. So that's going to be the general solution to the equation given above. All right, so now just the thing to remind yourself is the choice of the solution form for the particular solution is going to be based on the structure of the right-hand side. Okay, and I'll talk a little bit more about that after we work one more example. Another thing to say here is that obviously we can determine the C1 and C2 coefficients if we have initial conditions, which means we would have something that would specify y of, let's say, 0 equals some number, let's say 7, and y dot of, let's say, 2 equals 5, for example, right? These are just problem specific, but with those, we could then go in and plug those in and solve for C1 and C2. So again, we did that in the prior lecture, so I'm not going to tackle that here. Okay, as our third example, I've got the same left-hand side as I had before. The right-hand side, though, is a 3 times the sine of x. Okay, so it's now a trigonometric form on the right-hand side. I left the solution, the homogeneous general solution, C1e to the minus x plus C2e to the minus 2x there, again, because that is solved the same way. And so I really want to focus on the solution due to the non-zero d of x that equals 3 times the sine of x. So following in the footsteps of what we did before, we need to develop what we might call our again, particular solution structure. And because we have trig functions, we're going to follow in that vein. So I'm going to say y sub p is equal to a times the sine of x plus b times the cosine of x. Okay, so that's a general sum of a sine and a cosine term. And again, using the method of undetermined coefficients, I am going to find what a and b are. Okay, so the first step in doing that is looking at what the first and second derivative of y sub p are. Okay, so y sub p dot is going to equal, well, if I have a times the sine, well, the derivative of sine is cosine, so I'll have a times the cosine, a cosine of x, and then I have cosine of x as the second term. Derivative of cosine is negative sine, so that'll be minus b times the sine of x. Okay, so that's the first derivative. And the second derivative of y sub p is going to be, well, now I have cosine in the first term. Derivative of cosine is negative sine. So I'm going to have negative a times the sine of x. And then here I will have on the second term, the derivative of sine is cosine, and I carry the negative along with it, so minus b cosine of x. So that's the first and second derivatives. Now I need to plug those into the original differential equation left-hand side. Okay, so it's going to take a little bit of writing, but I'm going to start with the second derivative. So I'll have negative a times the sine of x minus b times the cosine of x. Okay, and then plus 3 onto the first derivative. So that's a cosine of x minus b sine of x, and then plus 2 times our original y sub p, so that's going to be a times the sine of x plus b times the cosine of x, and all of that has to equal 3 times the sine of x. Okay, so this expression is that expression. All right, so that's a lot of stuff going on the left-hand side, but it's really not that complicated. I just got to do some collection here to collect the cosine and sine terms. Okay, so doing that, I'm going to end up with a minus 3b onto sine of x, and then plus b minus 3a onto cosine of x has to equal 3 sine of x. Okay, so now I see I have two equations and two unknowns. So I'm going to have a minus 3b has to equal 3, and because it's multiplying the sine, and we have a sine term on the right, and the b minus 3a has to equal 0. Okay, so those are my two equations and my two unknowns. And solving, I'm going to get a equals 3/10 and b equals negative 9/10. Right, so those are what I'm going to get when I solve that system of equations. Okay, with those coefficients, we can go ahead and write. This is going to be 3/10 times the sine of x minus 9/10 times the cosine of x. And that is the particular solution for the non-homogeneous case. All right, so then based on that, we can write the total general solution for the non-homogeneous equation is the combination of those two. Because remember, if we have, I want to just re-emphasize this, if we have a solution to the homogeneous case, which is the y sub h, and we have a solution to the a particular solution to the non-homogeneous case, then another solution is the sum of those two solutions, right? So we can go ahead and write that down. So that was the, what we're doing here with this construct and this method. Okay, so our general solution then is C1 e to the minus x plus C2 e to the minus 2x plus 3 over 10 times the sine of x minus 9 over 10 times the cosine of x. And once again, if we had initial conditions, which means we had the function value and its first derivative specified somewhere, then we could use that information to determine what C1 and C2 are. But like I said before, that was done. That method there's nothing new there that we haven't done in the prior discussion, so we're not going to dig into that now. All right, so the final point I do want to make is for these examples, we had a right-hand side that the first time it was an e to the x functional relationship, and the second time it was something that looked like a quadratic or a polynomial form, and this time it was a trig form. And so it turns out, because this differential equation is linear, we can solve a system that might look something like, I'll go ahead and put a line here, and if we had a system that looked like y double dot plus 3y dot plus 2y equals, let's say, something like 2e to the 3x plus 4x squared plus 3 times the sine of x, right? Well, the first example was something that had a right-hand side like that. The second example had a right-hand side like that, and then this example had this right-hand side. Well, because it's linear, we can actually form the solution for these, this complicated thing, right? If you just had that right-hand side and we started with that looks horribly complicated. But it turns out we can break it down into 3 different cases, find 3 different general solutions, and add those together. And that would give us a solution to the entire differential equation. So that is an important aspect of how these linear differential equations work. So something good to keep in mind. All right, so that's all I've got for this particular segment. I just wanted to talk about these non-homogeneous cases and give you a particular solution method for, again, let's say this second order linear non-homogeneous ordinary differential equations, and in this case with constant coefficients, at least on the left-hand side, and the right-hand side, because they're non-homogeneous, we have a d of x that's non-zero. And that's where all the excitement for this session came from. So thanks for listening, and have a wonderful day.